Welcome back to the third part of this problem. We remained it at 1 over a plus 1 over b plus 1 over c is equal to the square root of this number. And if we substitute this value in our inequality, we will have that a over b squared plus b over c squared plus c over a squared is greater than or equal to this square root. So we will square on both sides. I have decomposed this square, which is greater than or equal to this. After we did this, we can simplify these three terms. Now I have grouped this one with this one, this with this, and this one with this one. So these three terms with these three terms in these brackets. Now I have subtracted these three terms from these three terms, and I factor this out, and we remained it that this term is greater than or equal to 0. I have amplified these fractions, and then I subtracted from these fractions, so we have AB minus BC over this, plus BC minus AC over this, plus AC minus AB over this is greater than or equal to 0. And now I want to put the condition that A is less than or equal to B, which is less than or equal to C in this order. Now this difference becomes C squared minus A squared all over 8 to the 4, plus this difference, which is this, and this is this, and then we will copy this relation. Now I will note this sum to be S, and now we will analyze every term from this. Now the sum of this, which is greater than 0, will be proven in the next moments. Now let's take C squared minus A squared over a to the 4. This one is greater than or equal to 0, but not greater than 1. Now a squared minus b squared all over b to the 4, obvious, is less than or equal to 0, and then b squared minus c squared all over c to the 4, obvious, is less than or equal to 0. Now we will draw a line to conclude something. Now let's compare these fractions. Look at the first. The numerator c squared minus a squared, in our case, will be greater than the absolute value of the numerator a squared minus b squared, which will be b squared minus a squared, because as we know, a is less than or equal to b is less than or equal to c. And here also the absolute value of b squared minus c squared, which in our case will be c squared minus b squared, will be less than c squared minus a squared. So this is the largest numerator, and now the denominator will have to be the smallest, because a to the 4 will be less than or equal to b to the 4 will be less or equal to c to the 4. So we conclude that this fraction c squared minus a squared all over a to the 4 will be greater than or equal to the sum of these two absolute modulo fractions. So the absolute value of this fraction plus the absolute value of this fraction will be smallest than this fraction. Else we will have here a negative fraction and a negative fraction if we are not adding the absolute value. And because this is true, it follows that S is positive. So our business with this sum is done. We have to find that if this sum is greater than or equal to 0. If this is true, we have completely solved this problem. We have to prove that AB minus BC over this plus BC minus AC over this plus AC minus AB over this is greater than or equal to 0 from here. The first fraction is equal to B times A minus C all over B squared C squared is equal to A minus C all over C squared B. We simplify from here. The second fraction is equal to C times B minus A all over c squared a squared, which is equal to b minus a all over a squared c. And then the third fraction, ac minus ab all over a squared b squared is equal to a times c minus b all over a squared b squared, which is c minus b all over b squared a. In our case, a is less than c, so this fraction is less than 0, is negative. B minus a is positive, so it's greater than 0, and c minus b also will be positive. Now if we want that this sum to be greater than 0, we will check that c minus b over b squared a plus b minus a over a squared c to be greater than or equal to the absolute value of a minus c all over c squared b. It follows that c minus b over this plus b minus a over this will be greater than or equal to c minus a over this if we want to be true. But here we will need a formula that x over y plus z over t, let's say, will be always and always greater than or equal to x plus z over y plus t. Remember this formula. This formula is very useful at Olympiad problems. But in our case, we'll write c minus b all over b squared a plus b minus a over a squared c surely be greater than or equal to now the sum c minus b plus b minus a all over b squared a plus a squared c, which is equal next with c minus a all over b squared a plus a squared c. So we clearly know this one. Now I can see that the numerator from here and the numerator from here are equal. And if we will prove that this sum, which is obvious greater than this, and this fraction will be greater than this fraction, it follows that this sum will be greater than this fraction. Let's get started. Now we can multiply by 1 over c minus a, such that 1 over b squared a plus a squared c will be greater than or equal to 1 over c squared b. Now let's see. It follows that b squared a plus a squared c will be less than or equal to bc squared. If this is true, our problem is solved. Now let's see if b squared a is less than bc squared. We can divide by b, so we have that ab is less than c squared. Is this true? I don't know, but if we make the ratio a over c is less than or equal to c over b, we will see that a times b in this order is less than or equal to this. Now let's analyze these fractions. A over c always will be less than 0, and here will be positive, so this is true. Sorry, 1. Now we check this one. A squared c is less than bc squared. We will divide by c, so we have a squared is less than bc. And now let's see if this is true. We have that a over b, if we decompose, is less than c over a. A over b always will be less than 1, and c over a will be greater than 1, so this is true. So we have proved this inequality, so the inequality completely was solved. Yay! If also you have an interesting math problem, you can contact me on this email and I will respond you. And thanks for watching.